Our third in the trio of carbon-constrained fossil energy is Mike Celia. He's a longtime colleague of Bob's within the Princeton University Carbon Mitigation Initiative project. And Bob regards Mike as the world's foremost authority on CO2 leakage science.
It was maybe 18 years ago or something. I was here at Princeton, and I had several visits from Rob and Bob Williams, Rob Sokolow and Bob Williams. And at the time, I was spending most of my effort looking at fluid movement underground, but I was interested in shallow systems, you know, like soils, water and air and plant root uptake and those sorts of topics. And so Bob comes in and says, hey, why don't you look at carbon storage underground? And I'm thinking root systems or enhanced vegetation growth or something like this. But it turns out, of course, he had in mind CCS, meaning going a few kilometers deeper than the surface. And that, in fact, is how I first became interested and involved in anything related to CCS. It's really because of Bob and, of course, Rob as well. And that has led me to some fantastic experiences. And I'll just say that from my perspective here at Princeton, there are many really terrific people across this campus. But you know, whenever I'm feeling like, you know, I really want to hear something interesting that I'm sure that I myself would never think of, it's just a walk to Bob's office, because he's always full of just amazing ideas. And I walk away saying, wow, this is just, you know, something that I would never have thought of, but it's really interesting. And you know, that has had impacts on, for example, the way that my PhD students have done their work, with Ben Court, for example, spending a whole thesis looking at water issues and things like that. So Bob, from a personal point of view, a big thank you for all of your influence on me personally. And anyway, of course, I could spend the next 20 minutes telling similar stories, but let me get on to this topic, which is one that Bob asked me to say a few words about. The introductory comment I've already made, and I'll restrain myself from making any more. We've been interested in sort of the environmental impacts of very large-scale CO2 injection. If you're going to do CCS and you want to have an impact on the climate problem, you have to put a lot of CO2 underground, and probably in many different kinds of formations. And we have focused a lot on injection into deep saline aquifers, meaning deep formations that are filled with salty water, for which we don't have any use at the moment. They're well below drinking water zones. And most estimates say that we need to put a lot of CO2 into those kinds of formations if we want to actually have a significant impact on the climate problem. So coming from an environmental engineering perspective, you know, our interest was, if you do that, are there environmental impacts that we might anticipate and try to then, you know, design for beforehand. And one of the things that comes up, and I'll show you in a minute, is that a major concern is if you put all of this CO2 underground, how much of the CO2 or other fluids are likely to leak out of the formation you're injecting into, and maybe into places where you don't want them. So in the US, for example, EPA has written regulations about CCS and CO2 injection, and those were all written by a group whose responsibility is protection of underground drinking water. So it's a shallow zone drinking water aquifer problem, and you need to make sure you don't damage drinking water, all right, at least in this country. So, so we set about thinking about the leakage problem, and it turns out that in North America, especially in North America, that we have a lot of old oil and gas wells in these deep sedimentary basins that happen to be the same places that we identify good targets for injection of CO2. So it's hard to avoid the question of, if I put a lot of CO2 underground, am I going to get an unacceptably large amount leaking perhaps along these old wells, of which there are millions of them in North America? And we set about to answer that question. And that's sort of what I'm going to tell you about in the next 10 or 15 minutes. So here's the cartoon sketch. I'll try not to hit a bad button here, but I probably will at some point. So we do an injection into a deep formation here, and the issue is, are there pathways? either faults or old wells that could allow leakage, in this case, for example, into drinking water aquifers, which, as I said, is sort of a principal concern, certainly in the U.S. The reason that this comes about, this is a map created for a special report from IPCC in 2005 that focused on CCS, and the darkness of the red scales with the number of or the spatial density of wells. The darkest red, which occurs along sort of the mid-continent of North America and other places in these deep sedimentary basins, are spatial densities of 2 to 6 wells per square kilometer. All right? And the next lowest red is about half a well to 2 wells per square kilometer, et cetera. So with these kinds of pieces of information, it's hard to avoid the question of what do we think is going to happen. I'll give you an example. Here's, we did a lot of work in Alberta for various reasons. Alberta, of course, is the energy producing province here in Western Canada. Its capital is Edmonton. And if you go just to the southwest of Edmonton, you find 4 large coal-fired power plants, collectively emitting about 30 million tons a year. And if we were going to do CCS, this seemed like a logical place to think it might happen. So the area in yellow here, which is about 50 kilometers by 50 kilometers, is one that we studied in some detail. And if you just take the outline here, this is now the full white outline, corresponds to 50 by 50. Every one of these dots here represents an existing oil and gas well, and I'm sure you can count them up quickly, and you'll get about 1,250. And if you divide 1,250 by the area, which is 50 by 50 is 2,500, you get about 0.5 wells per square kilometer, which you'll remember was the low range of the second darkest red. So it appears that this is not an unusual case, all right? Anyway, that's what we've got. So suddenly this becomes our sort of our cartoon image. If I do an injection into a deep formation, might it be the case that either the CO2 or the brine I displace leaks along some of these old wells, and if so, where does it go? Into other formations as you go up the stack, into drinking water zones, back to the atmosphere, et cetera. So this became the question we wanted to answer. And to do that, we had to go back and sort of learn about oil and gas wells. Luckily, we have a great partnership with BP, so there's lots of ways to get this kind of information from real experts. But the upshot is that the first thing we do in my group, and you can forget about the equation I know that we talk about physicists, so physicists in the room maybe will like the fact that in my group we like to do reduced order models, all right? So in fact, sometimes we do things where we can even get analytical solutions. It's a lot of fun. In any event, we have an injection, we have a CO2 plume that develops. CO2 is less dense than the background salty water I told you about, so it moves up by buoyancy, et cetera. You can describe all of this mathematically. And then we're interested, if you remember the cartoon, I'm interested in multiple geological layers with wells that might be leaky and that have some kind of complicated structure to them, and another equation to tell us about how things move. And at the end of the day, you can put all these things together into a model, which is what we like to do in my group. All right, so I'm minimizing this, but this is sort of how we spent a number of years, is trying to figure out how to put together a model that would give us the information we want, which is if I do a large-scale injection, how much CO2 and brine do I expect to leak into places where I don't want it? All right, and it turns out that we couldn't find any off-the-shelf software that would allow us to run this kind of thing, so we developed all of our own. And then most of this was done by a mathematician, Jan Nordbotten from the University of Bergen in Norway, and he and I wound up writing a book about this. I'm sure you'll all run out and buy it immediately after, I hope at least. In any event, you can find all the details in there, okay? That's part of the story. So at the end of this exercise, we had a model that I thought was really cool. I liked it a lot. The problem is that we had no information about old wells. Okay, there's some number of millions of old abandoned wells in North America, and we would like to know what's the state of the well, something about the hydraulic properties of the materials in it. Is it easy to leak or difficult to leak, or is it plugged properly? And it turns out that quantitative information was very difficult to come by. So we wound up being in the fortunate position that we could partner with BP and also with Schlumberger, and they were willing, in this case it's a Schlumberger rig, to go out and re-enter some old wells and do a whole bunch of downhole testing. All right, so, and it's just a fantastic technology. So, in this case, Schlumberger went down about 2 kilometers, and then they have this tool that they can turn sideways and drill a core through the casing, through the cement that's outside the casing, and into the rock. Grab the core, pull it up 2 kilometers, and hand it to you at the surface. It's just fantastic stuff. So here you see an image, for example. Here's the casing, here's the cement, and here's the shale rock that was outside of the casing. And then you could analyze these things in various ways. They also did something we were more interested in, which is larger scale hydraulic testing outside of casing to give us a sense of what the larger scale material properties might be. All right, and all this was really nice. And I had a student at the time who did a lot of analysis of the data. And this could give us, at the end of the day, by doing various inverse modeling, estimates of the effective permeability of the well material outside the casing in the interval that the measurement was done. All right, so suddenly we finally had at least a couple of data points that would tell us something about permeability. And if you know anything about this, this is actually a pretty high number. 170 millidarcy is sort of a good reservoir, I guess. So it's not what you expect for the cement material that's outside the casing, but nonetheless, there it is. Now, the other thing that happened is we were able to get data from other sources as well. In conjunction with Denise Moserel, Denise is here, we had instigated, or actually the graduate student Mary Kang here really was responsible for asking a different question about wells, but one that turns out to be relevant to my story, which I'll connect in just a minute. But her question after taking a course with Denise on methane was, hey, you talk about these old wells all the time. Are they leaking anything right now? And why don't we just go out and make some measurements in the neighboring state of Pennsylvania, which has lots of old wells, to see whether anything's coming out of them? And in this case, the concern was methane to the atmosphere. Are old wells a source of any methane going into the atmosphere? And can it, sort of explain some of the difference between top-down, bottom-up measurements for methane? So it's not related to CCS, it's methane. And this is a flux chamber to measure. There's a well inside here, and you can measure how much methane is coming out of this well. All right? It's a very nice project, but it's a separate talk. Pennsylvania has lots of very interesting looking wells, probably more than 500,000 of these old wells in various places. So it turns out to be an interesting study area, and we published a couple of papers on this about the methane emissions. If you're interested, send me an email. I'm happy to send them to you, or you can find them online. But the other thing that we did, which now comes back to my carbon story, my CO2 story, is with a little bit, again, the physicists will like a little bit of reduced order modeling, we could take the leakage measurements, and with a little bit of inverse modeling to think about what's below the ground, infer the effective permeability of the leakage pathway for the fluid coming up the well. All right, so it gives us another set of data to estimate these hydraulic properties of old wells that we were interested in. And so here are some of the initial data that we had. These are about 30-something wells that we initially measured. And here's effective permeability. This is millidarcy going from 10 to the minus 4 to 10 to the plus 2 here. That's about the range of the data. So about 100 millidarcy on the high end and a very small number, 10 to the minus 4 on the low end. All right? If we go back and remember this guy, right from the re-entering the old well, this will plot about there. And if we look at all the other data from re-entering old wells, it plots along here. And it turns out in the meantime, Steve Bryant and his group at the University of Texas at Austin had done a separate analysis of some other data sets, and they estimated permeabilities kind of in this range. All right, so between all of these studies, we went from having no data to having a few hundred data points. And then I could take the leap and say, you know what, let's assume the statistics that I see from these measurements will apply to my case in Alberta. All right, that's the best I can do. By the way, Walter Crowe here, the first author on this paper, is from BP, and this is one of a bunch of joint work that we did that was quite beneficial. All right, so if I go back now to the Alberta case, of course you have to remember that I might have 1,250 wells, but they all go to different depths. Okay, so you have to think about the vertical profile. We need a stack of all the formations that are permeable and impermeable, permeable, impermeable, et cetera. All these things go into our model. And then what we do is to assign to every one of these wells and segments of wells a permeability value, for example, that comes from the probability distribution derived from our data. So it's a kind of stochastic analysis. And that means that, so in this case, we ran 1,000 realizations using different realizations from the statistics of our input. And this is a plot, for example, a log plot of the fraction of the injected CO2, in this case injected in the middle of the domain, that leaks after 50 years of continuous injection. All right? So these are 1,000 different data points binned into a histogram. And you see 950 of these fall below 0.02%. A very small fraction of the CO2 that's injected actually winds up leaking in almost every one of these based on the statistics from the measurements that we made. All right? And the upshot is that with our current best estimate of permeability statistics, an acceptably small amount of CO2 leaks at what I would consider 95% confidence, 95 out of 100, after 50 years of injection. And we're going and looking at this for other systems at the moment, but this is counter to my initial expectation, I have to say. I thought wells were going to be a much bigger problem. These numbers say that what we see will be acceptable in regard to climate considerations and should also be easily manageable in terms of any concerns about water resources. By the way, the amount of displaced brine that leaks is significantly less than this amount, all right, just for context. So the upshot is that the leakage of both CO2 and displaced brine along old wells appears to present minimal risk as a kind of general conclusion. And this is one of a small number of risk factors that have been considered potentially important for this technology. And right now, it looks like the numbers are coming out in favor of the technology. So general comments, these fit into a lot of what other people have said. CCS is still central to low-carbon future projections. We've already heard that this morning. In case you're interested, capacity estimates indicate that we have enough storage space, certainly in the US and in many other parts of the world, for large-scale CCS to be implemented. The technical issues like the ones I just mentioned appear to be manageable. The pace of development is much too slow for this to ultimately have a big impact on the climate problem. And my last bullet here really gets me back to Bob, which is creative approaches to increase the pace of development are needed. And anytime I want to hear something about a creative idea to make this go faster, I take another visit to Bob's office because he's always got ideas on how to make it happen. All right? So anyway, thanks for your attention. Yeah, so what we want is a formation that is thick and permeable and aerially extensive, so it's easy to get a lot of fluid in without getting excessive pressure buildup. And it's overlain by a good low permeability cap rock that stops the buoyant CO2 from going up. All right, and if you have that, pretty much you win the game.
How about earthquake areas?
Well, of course, you don't want to inject into an earthquake area. The other, really there are two issues that usually come up. One is leakage. And the second one, which I purposely avoided, was induced seismicity, which is if you put a lot of fluid underground and you increase the pressure, you can read lots of things in the literature in the last 5 years about induced seismicity. My own sense of it is that what you need to do to zero order is to keep the significant pressure pulse out of the basement rock, because there is where most of the felt earthquakes originate. The faults tend to be at or close to critical stress, so it doesn't take much pressure to make them slip. And that means that, that when you're injecting into a sort of a sedimentary stack, that should be probably part of your thinking.
So the USGS study of 2012, I think it was, talked about the injection of fracture material into into, does that drive into this or actually?
They wind up going together because most of what you read about in terms of induced seismicity would be involved either with geothermal projects, which tend to be very deep injections into the hot basement rock. Okay, so and the other is the injections associated with fracking, but it's not the fracking process itself. It's the injection of the collected wastewater that comes back after the fracking that has to be disposed of, and you get large volumes of aqueous fluid that winds up being injected. And if you do that in a bad place, then you can wind up with felt earthquakes. And you see that these days in Oklahoma.
One more question.
Many years ago, Ed Teller proposed a method of making large underground cavities in storage of whatever one wishes. I hope nobody is proposing reviving that one, are they?
That would be a very, very big cavity.
But is anyone in this business actually proposing to do that?
Not that I've heard of, no. You know, there are lots of geological reservoirs that we understand pretty well, and that are sort of obvious targets for doing this.
So one more question. Yes, please.
So you mentioned the risk of CO2 leakage and brine leakage is very low. So I was wondering if today we want to store most of the emission, so we create a lot more large-scale CCS project, would that increase the leakage risk? Because
Yeah.
we have a lot more wells.
Yeah, so I'll give two quick answers to that. First of all, we've done a fair amount of analysis along with Carl Bandilla, who's in the room somewhere, and others in my group, thinking about sort of very large-scale deployment. Like if you captured everything from the Illinois Basin, which is a few 100 million tons a year, and wanted to inject that into formations in the Illinois Basin, what does the system wind up looking like? All right, and that actually appears doable based on what we know about the system. More generally, I think it is it's actually a more involved question about which I think is an interesting question. If in fact we had wild success with CCS, all right, what does it look like, and what does it mean about how the risk profile for injection evolves on sort of decadal timescales? Because early on, we always take the best formations, right? So 30 years out, maybe the industry is going great guns, all right? We've already used up the best space, and how does that risk profile evolve with time? So in the case of Alberta, you know, we'd be choosing different formations along the stack, but they would always be less ideal than the first one or the previous one chosen, because we always choose the lowest risk as the next one. And it's an interesting analysis that I've wanted to do for a while, but I haven't done. What does wild success look like, and is there a limit when you come back to a risk consideration? Yeah.
Thank you, Mike.
Thank you.